It should be okay. I should go live. Okay. 2, 3, 4, 5 seconds. Okay. Okay, 5 seconds. 5 to 6 second delay. So this week I will cover. Today I will cover the graph. In the following week, the problem all are about the graph. Before I start this week lecture, I think the assignment, quite a number of students have a problem about the double hashing under the open addressing. Something I need to point out. Yeah, although this one only 4 points, actually is you will find that actually when you start delete a key in under the open addressing, the problem become not that simple. Yeah, a few things you need to take notes in that question. I'm asking you to count the key comparison. The key comparison means that you really have the key. Whenever the input key, the search key, or the insert key compare with the key in the slot, then that is considered key comparison. Whenever you do so, you definitely have some if-else statement doing such a comparison. When you do so, you just simply count increase by 1. When you didn't do that, then don't increase your count. Like, not counted as a key comparison is like when you compare the slot is empty or not empty. You only check the slot is empty or not empty. There's no key comparison. When there's no key comparison, it's not counted. Of course, it's not key comparison. I think this one don't need to explain. I hope you understand what is key comparison means. That you have an input key and you have the key in the slot, you compare, then that is key comparison. Okay, then I think another issue is like when you delete a slot, you will make a marker that says it's considered this particular slot is already deleted. We will not access, although we not really go and clear or free the memory in that slot, but you should not, after that, you should not try to access it. Then when you're trying to insert a new key, you prone and prone, you need to understand that you may reach the deleted slot, you may reach an empty slot. There are two different scenarios. When you reach an empty slot, okay, you can insert the key straight away, no problem. If you didn't, before that you didn't encounter any duplicate repeated key, then you can straight away to insert that particular key. But when you try to insert a new key, you reach a deleted slot, you cannot immediately insert the key because you don't know whether after this deleted slot behind, whether there's a same key, there's a duplicate key or not. You need to check first. That means that you need to go and prone the following slot, alternate slot first. And if you find there's no duplicate, when you check, you didn't find any duplicate slot, and you reach another empty slot, or you already search through the whole table in this manner, you already check one round, let's say your table is almost full, then there is no such thing. Then you qualify, you can insert the new key. Then you need to go back to the first deleted slot, the first available slot, and insert it. Yeah. So you may encounter 2 deleted slot, you may encounter 3 deleted slot, but which one you should insert? Of course, it's the very first one you encounter, not the second one. Not make sense why you insert in the second one. We're trying to insert the key as early as possible, so that later the search time will be shortened. Yeah. So that is the idea behind. Yeah, of course you can override, like here I already mentioned. Yeah, you can override it. Yeah, when a new key is inserted to the slot, no problem. You can just simply override it. After you override it, this particular slot no longer considered as a deleted slot because you're already in use. and you can search it, you can use it, you already override it. Yeah, so you need to update the marker. I think that is the few common issue people encounter. Yeah, of course, when you search the key, when you check whether it's the duplicate key, you still use the hash table, the process to prompt and prompt and prompt. You cannot trying to check the whole table. I already put the table quite large. Then in practice, the table can be 1,000, 10,000. Just like this week lab, when you use the linear search, you will take a lot of time. Just like this week lab, I think the first two question is a something search. The question one is linear search. The question two is some kind of a binary search. Then the third one, I give you a sample input which is 500,000. Another one I think is 1 million. You will find that the first one you will take some time to get the result. You may depend on your computer, but definitely you will run much longer than the second question. The second question I sort out the data. First I use the quick source. Quick source will cover in the next level, but I'll already give you the implementation. You don't need to bother how I sort the data. I already sort it out using the quick source algorithm. Then after that you find that you can accelerate your search time. From linear to logarithmic. And then when you supply your input is 500,000 or 1 million, you'll find that it's a lot faster. It's almost instantly you get the output. Yeah, but the first one you may take, some people take 5-10 minutes, they just saw the result come up. Depend on your computer, but definitely slower than the question 2. Yeah, so that is the idea that why we want to know analysis the algorithm, why we want to improve the algorithm, the time complexity from linear to logarithmic if possible, because the computational times is really improved significantly. It's not like few seconds improve. It's really improved a lot. When especially you supply a very large data, you wouldn't appreciate it's like when you supply your own input. Yeah, 2-3 input, nothing. Yeah, both are about the same because it's almost instantly you come out the result. That is what you will learn in this week lab. And also I think I think in the question 3 I just show you a trick that you will find that a lot of time you have some input. You have some input is very tedious, can be a lot of you need, like this one is like 500,000 input. It's not possible that you repeatedly key in 500,000 input. And sometimes you have very tedious input. There's a trick. You can save your input in a file and then use it to fit your program. You can use that trick to I think it's quite useful, especially when you want to test your program multiple times. You can pre-save all the input in a file and then every time use that file to fit it. And you also can have a output file. Instead of print out the output in the command line in the terminal, you can save it in a file so that you can compare the first run, the difference between first run and second run. I would say in the future is sometimes it's very useful when you encounter a very complex problem. Yeah, this is something you can use it. Just introduce to you. Okay, so this is something about the lab, the assignment. And then, okay, back to today graph. So today I will introduce about the graph. So today I will cover the graph and how to represent the graph. You will find the graph you can't really like binary tree or a linked list. You really can store the whole graph in the program, like what you see as a graph. And a lot of problems you don't have to do so. Yeah, so we will introduce 2 representation. One is adjacency matrix, the other one is adjacency list. Probably I think today I only can cover these 2. Yeah, if time allow, I will cover the breadth first search. If not, I will cover the breadth first search and depth first search on Wednesday. Then after I finish this portion, maybe this Wednesday or next Monday, I will release the next assignment. So please trying to start doing your assignment for. Yeah, at least you should log in and look at the question and then start try out a little bit. Take notes that that assignment, the invitation link is only can last for 2 weeks. You don't wait until last day you ask me to give you the access. Yeah. Then I know what you are trying to do. So graph, I think you may learn in discrete mathematics also. So it's just like basically it consists 2 components. One is the vertex, one is the edge, and finite set. All the algorithm we talk about, the input output, the algorithm is in finite set. So there's a set of a vertex and there's a set of a edge to form the graph. Then we use this notation to indicate the number of vertex. If V is represent a set of a set of vertex, then this notation is indicate the number of vertex. Same thing, if E represent a set of edge, some book may call it egg, some book can call link. Yeah, just like vertex, can be nodes, depend their application, depend the problem. Yeah, they may name slightly different, but actually they are talking about the same thing about the graph. Yeah, so edge is like those link, those edge arc to connect the vertexes. Then if this E is connect the X and Y, then it's like, yeah, then X and Y is in the V, is a set of vertex, is one of the vertex in the V, then E is the edge. Then this is represent the number of edge. Not surprising that it can range from 0 to the number of vertex times number of vertex minus 1 over 2. You can easily use one example to visualize it. Why is it so? Let's say I have 5 vertex. 1, 2, 3, 4, 5. You have that n vertex, n number of vertex in this graph. Then of course the minimum number of edge you can have is 0. No edge, just like what you see in this, no edge. All the nodes are a standalone. They didn't connect to any other vertex. So no edge. It is the minimum number of edge you can have, 0. Maximum is like, that means in this scenario, every vertex can connect up to 4. Excuse me. 1, 2. In 5 vertex, you can have 4 edge. Each of them can connect the other 4. That's why it's V times V minus 1 divided by 2. So everyone can connect. This one is already included. Yeah, definitely there's a repeated one. And this one is another 4. There are 2 already. I just need to add another 1, 2. Then this one already have 3. Then this one is here. So the total number you can have in this example is 5 times 4 divided by 2, which is 10. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 edges. You can try some example. You will find that it definitely is V times V minus 1 divided by 2. That is the maximum number edges you can have. Yeah. Then when they said the degree of a vertex is the number of edge incident to it. So in this, when they are all fully connected, all the nodes, the degree is 4. There are 4 edges incident to it. So that is it's just a terminology only. Sometimes we will use this term. Then you have learned about the binary tree. You can consider tree is a special case, is a special graph with no cycle. Yeah, because when you learn the binary tree is just one of the example of a tree. Yeah, tree can have a lot of child, more than one, more than two. Yeah, so let's say, yeah, but the tree definitely won't form any cycle inside the tree. No cycle. If any sibling they are connected, then they will form a cycle. Then this is not considered a tree. Tree, there's no cycle. Okay. So yeah. So that is a tree. But whether, yeah, then it's a special graph. Yeah. You can consider it's a special case in the graph. Then there are a lot of kind of a graph. It can be undirected graph. That means all the edge, there's no direction. They don't give any direction. That means A is connected to B. You also can say B is connected to A. Then you also can introduce some weight on the edge. Then it becomes weighted graph. Yeah, that means to travel, example, like you want to travel from A to B, yeah, there's some cost. I can use the weight to represent the cost. Yeah, so that I can know that if I want to travel from A to B through this particular edge, the cost is 7. If I travel from A to D to B, then the total cost is 5, 3 plus 2. If I travel from here to here, then become 5, which is lower. Yeah, so that sometimes some problem we need to introduce the weight into the graph to assist us to solve the problem. Then we also can introduce the direction. Then give each edge there's a direction. Then it becomes a directed graph. Then this one is considered as a complete graph. They are fully connected. So this is just different kind of a graph we can have for different problem. So if E is connect the X and Y is an edge in an undirected graph, then E is incidence with X and Y, then I can say X is adjacent to Y and Y is adjacent to X. Yeah, if it is an edge of undirected graph, then I can say so X is adjacent to Y, Y is adjacent to X. Then if E is unordered, then G is undirected. If otherwise, G is directed graph. Yeah, if another one is directed graph, if E is XY is an edge in a directed graph, then that means Y can reach from X through one edge. Then we can set Y is adjacent to source X, but it may not means that X is also adjacent to Y. Meaning Y can be reached from X. That means this is, let's say I have one vertex is X, I got another vertex is Y. Then there's a directed graph. You only can from X to Y. That means Y can be reached from X. But doesn't mean in this diagram, Y cannot go to X. You cannot reach, X cannot be reached from Y through one edge in this example. In this example, I didn't draw another edge. In such a situation, you only can set Y is adjacent to source X to X. Y is adjacent to X, but you cannot set X is adjacent to Y for a directed graph. Okay, so there's some terminology you need to know. Next one is a path. A path is a sequence of a distinct vertex, and then each adjacent to the predecessor except the first vertex. The first one don't have the previous one. So for example, in this example, I got A, B, C, D. Let's say to form a path A to B, A to B, B to D, D to C. Then this one form a path. Then the each adjacent to the predecessors. This one C is adjacent to D. The previous one is D. Then this one adjacent, the predecessor is B. B is adjacent to the A. But A is the first vertex, except the first vertex. A, of course, don't have any predecessor. Yeah, no more. This is the very first vertex. So in this path, you got 1, 2, 3, 4. You have 4 vertex. That means you have 3 edge. Yeah, the number of vertex is the edge plus 1. That form a path. Then if it's a cycle, then it's a path containing at least 3 vertex, such that that means at least you need 3 to form a cycle. You need at least 3 vertex, such that the last one, from here to here, from here to here, then the last one will go back to the first one. Yeah. So in this example, let's say you got 4 vertex, then your A to B, B to D, D to C, C back to A. Then they form a cycle. Then the number of vertex is equal to number of edge. 1, 2, 3, 4. 4 edge, 4 vertex. They form a path. They form a cycle, sorry. They form a cycle. Okay? So an undirected graph, we said an undirected graph is connected if there is a path from any vertex to any other vertex. Or all the vertex you need to consider. That's means you need to check all the vertex. Any vertex to any vertex can reach any other vertex. So I need to check all the vertex to make sure that they are connected for undirected graph. Same thing, if in the directed graph, then we said it's strongly connected. That means there's a path from any vertex to any other vertex. Simple example. If I have one node, then for example, it's the undirected graph. If it's undirected graph, just now the 5 vertex one. If I said they are connected, yeah, this is connected. If there is a path, yeah. So if this is the I think I don't need so many for undirected graph. I think four edges. 4 edges is good enough. This one can be erased. Yeah. In this case, this undirected graph is connected because you always can any vertex. You need to check every vertex. You need to check every vertex and make sure that all of them, you are always able to find a path from this vertex to any other vertex. All the cases you need to check through. So this one is true. This undirected graph is connected, but this one is not. Yeah, even this one, yeah, if I add another 2 more vertex, let's say they are somehow like this. Yeah, then this one is not. They are not connected. Because this vertex cannot connect to any other. Yeah, this one cannot. From here to here, you cannot. There's no connection. Yeah. So that is for undirected. Strongly connected is for directed graph. Directed graph, then I need to definitely this one is not strongly connected. Definitely this one is not strongly connected. This one I need to give a directed graph. I need to introduce the direction. If this way, this way, this way, this way, not enough. I need to add one more. Then this one, yes, they are strongly connected because any vertex, I can find a path from any vertex to any other vertex. Yeah, definitely there's a loop. So you definitely can from any vertex to any other vertex. So in such a case, such a directed graph is known as strongly connected directed graph. Yeah. Then a graph is cyclic if it contains one or more cycle, otherwise it's acyclic. So this one obviously is a cyclic. There's a loop. There's a cycle. One or more. How many doesn't matter. As long as you can find one. As long as I find one cycle in the graph, then that particular graph is considered cyclic. 3 is the one you cannot find. 3, for example, if you have a graph something like this, something like a tree structure. Yeah, this one you definitely cannot find any cycle. If that is the case, then you can set this is a cyclic graph. Yeah, this one don't have. No matter how there's no, you won't be able to find any cycle in the tree. Yeah, this one is not. This one is acyclic. This one is cyclic. And this one I already explained to you. A complete graph on n vertex is a simple undirected graph that containing exactly one edge between each pair of distinct vertices. Then the total number of edges will be v times v minus 1 over 2. Yeah, this one is very useful. It's like in a lot of sector the problem we can formulate into a graph problem and then use some algorithm to solve the problem. For example, you want to search the shorter path from the source to destination, the path searching. Yeah, or you want to travel. Nowadays, I think our MRT station is getting more and more complex. We got the last time we only have the green east-west line, then north-east line, and then now you got north, the purple one, then got now town circle, all this. There are so many stations. You want to find how to travel from A station to B station. What is the shorter path? It's a graph problem. Actually, you can formulate as a graph problem. If you know the travel distance, that means the travel distance or the travel times from from each between two adjacent station, then that become a cost of each edge. There's a cost, the travel times or the travel cost. You can consider as a weight. Then you can do to search the shortest, cheapest cost to travel from A to B. Yeah, that is a typical graph problem. People study in chemistry, all this structure, atom, the bond to form all this. It can be form a graph problem. I think more related to you is computer network. Maybe later you will learn in the 2008, if I'm not wrong. Yeah, computer network. You can imagine that we have so many computers, and then all these computers connect to the switch to a router and then gateway to form the whole network. And then when you want to transfer your data, your package, your email from one point to another point, you need to go through how many switch router, and then you can reach the destination. And then how the router switch know that the best path for you, they involve some algorithm, graph problem algorithm. Yeah, have been implement in the switch and router. Just you don't know. Yeah. Then if you study in maybe CE student, maybe those from the triple E student may know the electrical circuit. You have so many components. All the component you need to connect it, together, and then eventually you need to squeeze all these things into a PCB board, like what you see in this diagram. It's an optimization problem. How you optimize it to such that you can put all the components and all the connection in this particular area. Yeah, so it's another graph problem. So a lot of daily life problem, if you formulate into a graph, then you will find that actually it can be solved. But you look at it, you may find that it's very difficult. But actually, after they formulate into a graph, a lot of existing algorithm can solve it. Yeah, maybe. We will introduce some of them in this level, and in the 2101, I think they will talk more about it. So the first thing is how to represent. Yeah, you want to solve the problem first, you need to be able to represent the graph in a proper way. Then before you can come out the algorithm. So you need the data is here. These are the data. This is the graph. How do I represent? How do I represent the graph to solve? Then I can easily solve my problem. So there are two. Here I only introduced two commonly used representation in graph, which is adjacency matrix and adjacency list. Which means that actually a lot of problem I don't really need to know I don't need to know the whole graph. I just need to know that each vertex and vertex, their connection, how who is their adjacency nodes around it is good enough for me to solve the problem. Because we especially in my part, we just need to know the nodes, the adjacency nodes, because we want to travel in the graph. A lot of problem, just like you learn in binary tree, you will find that your objective is, if you want to solve this problem, I just need to visit all the nodes in this graph once. Just like later, maybe on Wednesday, I will talk about the breadth first search and depth first search. Doing that is you just want to visit all the nodes once in certain order, by breadth first or by depth first. Then to solve this problem, then I just need to know that these nodes, what is their adjacency nodes. For example, this one, the only adjacent to 1 and 2. And then 1 is adjacent to 11, 2, 3, and 4. I don't need to know so much that 12 is so far away from 1. I don't need to know at this moment. I just need to know who is the address, who is his neighbor, and which one I have visit, which one I have not visit. Yeah, that is good enough for me to do the traversal. So in such a case, I don't really need to really construct the whole graph and store it. I just need to use the adjacency matrix or adjacency list to store their adjacency relationship. Is good enough. So that is the how we store the data for the graph. So what is adjacency matrix? Adjacency matrix is just a 2D array, which is the site is V by V, depend on number of vertex. If you have 5 vertex, that means it's 5 by 5. Yeah, 5 by 5. So it's 25 elements. And you can define it in this way. Then if there's the edge between UV, then the corresponding element in the matrix, adjacency matrix, will be equal to 1. Otherwise, you will let it equal to 0. Just represent that whether there's an edge or no edge, 1 or 0. Then if a graph is undirected, then you expect that it will be symmetric. Because let's say your U, I think I have an example. Okay, in this example, for example, this is an undirected graph. Since this is an undirected graph, 3 and 7 are adjacency nodes. 3 is adjacent to 7, 7 is adjacent to 3. So you're not surprising that at this 3, 7, this location, is equal to 1. Same thing for 3, 7, this location is also equal to 1. And you look at this matrix, this 12 by 12, because I have 12 nodes, so the adjacency matrix is 12 by 12. In this 12 by 12 matrix, you can see that this upper triangle and lower triangle, they are symmetric. Yeah, you can see that they are symmetric. This one here, there's a 2, 1, definitely there's a 1, 2. Yeah, they are symmetric. Yeah, definitely they are symmetric for undirected graph. So if a graph is directed, then may not be symmetric. If they are symmetric, which implied that this graph definitely is, this directed graph definitely is look like this. If they are symmetric, that means all the nodes is bi-direction. Yeah, in the directed graph. Yeah, if you have such a graph, you expect that your adjacency metric definitely is symmetric one. Only in this scenario is symmetric. Otherwise, it won't be it may not be symmetric. It will not be symmetric. Only in this scenario that every pair they have two edge. One is from A to B, the other one is from B to A. Then in such a case, then your metric is symmetric. Otherwise, for directed graph, your adjacency metric will not be symmetric. Only in this scenario is symmetric. Okay, so to the advantage and disadvantage of adjacency metric, advantage is you can instantly access. If you want to check whether any two nodes in the graph are they adjacency nodes or not, using the adjacency metric is very easy to access, because you just need to tell me the ID, like 37. I simply check whether there's an edge or not. I can instantly find out the answer. So that is the advantage to use the adjacency metric. The drawback is like, you can see that in this particular graph, most of the time you use so many space just trying to store zero only. Yeah, you can see this area, there are a lot of zero because they are not connected. There's no connection, then you will get zero. Then you will waste a lot of space just storing zero only. But the advantage, your space complexity is high, but your search time, if you want to check, if you're trying to search whether they are, or determine whether they are adjacent, the two nodes are adjacent or not, then this one will be much faster than the next one I'm going to introduce to you. Another one is adjacency list. Adjacency list is like something like the close address hash table. Is like there's an array. You have an array, like this example, you have 12 nodes. So is an array represent the vertex. So you have an array 1, 2, 3, 4, 5, 6 to 12 to represent the vertex, and then each vertex come with a linked list to list all the connected vertex to it. That's in all the adjacent nodes to the vertex, to that vertex, will be stored in the linked list, along the linked list. Just like example, maybe 1 is adjacent to 11, 2, 3, 4. So you can see that 2, 3, 4, 11 will be stored in this linked list. For 2 got 1, 5, 6, 11. Yeah, 1, 5, 6, 11 will be stored in a linked list. So that's when you got 12 vertex, you have 12 linked lists to store. Each of them will store all the adjacency nodes to that particular vertex. Then, not surprising, if you want to check, if you want to use this adjacency list to check, to assess whether A and B are connected or not. For example, you want to check two nodes, are they connect? Is there are they adjacency nodes or not? Then the search time will be in linear, because you need to search the whole linked list to check whether they are connected or not connected. But the advantage is the space complexity is lower. Probably is lower. Yeah, probably is lower. Later I will explain why. Yeah, the space is the number of vertex. The number of vertex here to form this array, plus the number of edge. This one will be the number of vertex. Here will indicate the number, each nodes, how many nodes will it be, is depend on number of edges you have. because if there's a connection, then you will store it. So if there's an edge, then you will store more nodes. If there's no edge, for example, in what situation the linked list can be empty? If you have such a graph. Yeah, if you have such a graph, then the adjacency list is only have an array, no linked list. All the linked list is the null pointer. Empty linked list. Because there's no edge. So the space complexity will be V plus E. Why I say is it may be lower. You can think about it. Yeah, this is the extreme case that no edge means that empty linked list. Then the space you will use is only the V. The space complexity is only the V. But if you have a complete graph, just now I already introduced to you, for example, this one, I need to draw. Okay, complete graph, they are all connected. Complete graph. How many edges are they? Is the V square. Is a V times V minus 1 divided by 2. You have so many edges. And then if it is an undirected graph, if this is the undirected graph, that means is like you can see 3 connect to 7, 7 FA connect to 3. So you can see here there's one node here. Here there's a one node here. So which is 2 times. So need to times the total number of edge times 2. Because you can from A to B, also can B to A for undirected graph. So you have 2 times edges. Then this one you plus the array plus this array got V vertex. Depend the V. Then total this whole thing, the space complexity is V square. Worst case can be go to this. Because here there's a V square. This one is V, not important because you have a V square here. Yeah. So the adjacency list is lower. May not be true. In the worst case scenario, it may go to square. Yeah, in the best scenario is no edge. The space is the smallest one. It's just a V only. You only create an array. All the linked list is null pointer. Is point to null. No nodes inside. In each linked list, nothing inside. Then another extreme is the complete graph. When it's a complete graph, then you can go to V square. Okay? So that is the adjacency list. So if further we want to represent a graph with a weighted graph, then you instead of just now is equal to 1 or 0 in the adjacency list. Adjacency metric. Then instead of store 0 or 1, we can introduce the weight. We store the weight in the metric. Yeah. Then if there's no edge between UV, then you can assign. Sometimes we will use 0. Sometimes we will give a very, very large number. Of course, you won't really store the infinity. You will store some unreasonable large number to indicate that not possible. Yeah, it's not possible. Sometimes, for example, you want to find the minimum cost, a shorter path between 2 nodes, but each edge there's a cost. Then you do not wish that to search the path which there's no edge. Then you will introduce a very, very high cost from those not connected edge, no connection nodes. You introduce a very large cost that you will find that those algorithms will not select that path because it's too expensive. So they will select the lower cost, which there's an edge connection. So that is like how sometimes they may not use 0 because you will put 0, then you very likely will choose that one because 0 is the lowest cost. Yeah. Sometimes we may introduce negative. Cost also can be negative. Yeah. Just like Most of the time, not that case, but certain algorithm they may introduce negative cost. Yeah, it's possible. Depend the problem. Then same thing, adjacency. If you store this weighted graph by using the adjacency list, then adjacency list you need to introduce the new member. Then you not only store the ID, you have another member. You will store the weight followed by the weight, the ID, the edge, the vertex ID, and followed by the weight. Just like this example. This is a weighted graph. Yeah. Weighted directed graph. Weighted directed graph. So not surprising that they are not symmetric. It's a directed graph. Yeah. And then since there's no cell connection, that means one is not connected to one itself. So the diagonal part is always 0 in this example. The diagonal is 0 because there's no such this kind of edge. If you have this kind of an edge, then the diagonal portion will not be 0. Okay, so since don't have, so not surprising here there's all 0. Then if it's in the adjacency list, they will indicate, for example, from vertex 1, you only can go to vertex 2. So adjacency nodes is 2. Then the weight is 25, and so on and so forth. So total I have 1, 2, 3, 4, 5, 6. 6 edge. So 1, 2, 3, 4, 5, 6. I have 6 nodes in this 4 linked list in total. Okay. So this is the, so you compare, for example, if you compare this example, no matter how, your adjacency metric is always 4 by 4, the number of vertex square. Yeah, the space you need. You always need to create such a big, and this is a small example. When your graph can be in practice, you can imagine I want Google Map. There are 100,000 of location. Then it's like 100,000 of nodes, vertex you need to consider. Then of course they will not really so silly to create such a huge metric. They will use other trick beyond the scope of this module. But you can think that if you really create an adjacency metric, the space can be very large in square, number of vertex square. Then adjacency list will be safer, will let you save more space, which is the V plus E. So if you have a very sparse graph, like this example, you only introduce 6 edge. Yeah, 6 edge. 6 edge. Somehow 6 space plus somehow, I think this is not very correct. 4 vertex plus 6 edge. Yeah, this one is square, will be 16. Yeah, then you can see that the space you need to use, compare these two, yeah, which one is higher. But depend your application, because if you want to fast access, fast access on checking, determine whether 2 nodes are connected or not, metric will be better. But sometimes it's like you just need to travel. You just need to travel. You just need to find the next adjacent, the next adjacency nodes. Then actually adjacency list is good enough, because from 1 I immediately know that the next one can be 2. I need to check all, but this one actually will take more times. You always will check, hey, are they connected? Is it non-zero? Is it non-zero? Is it non-zero? Yeah, you need to run a for loop to search all the vertex. But the linked list straightforward, just tell you that there are 2 nodes. Yeah, this one got 1 node. There's only 2 nodes. Yeah, this one you really need to go through along the whole row. Then you know who is their neighbor, who is not their neighbor. Yeah, it will take times. At least this one need to take 4 steps. When you got 1,000 of a vertex, 10,000 of vertex, 100,000 of vertex, you need to run a for loop to check through the whole row. That will take a lot of time compared to adjacency list. So there's the pro and con. Not really metric is better or list is better. Depend the problem itself. Okay. So in this lecture, I just give you introduce the graph, some terminology, the vertex, the edge. The graph can be directed, undirected, can be adjacent, can be weighted, can be unweighted. Yeah, then we look for a path, we look for the cycle, and so on and so forth. For the weight, okay. So then we introduce two adjacency metric and adjacency list, two ways to represent the graph. I think Wednesday I will talk about the travel. If you have a graph, a lot of time the problem is I want to visit every node once. Just like you will find that two breadth first search and depth first search I'm going to introduce on Wednesday, and maybe next Monday if I cannot complete. You will find that very similar to what you have learned in the binary tree. Or I would say that the implementation almost exactly the same. You need to use the stack and cube to solve that problem. Because actually they are I would say, to me, I see that is like actually they are using the same algorithm to solve the problem. You want to visit all the nodes once in systematic way to visit all the nodes once. Yeah, how are you going to do it? I will talk about it on Wednesday. Okay, let me answer some question. For the weightage, is there a specific location we have to use, or it is up to us what weight we want? Normally it's given by the problem. The weight is the cost. Okay, depend on the problem, people will define the cost. For example, if you want to find the shorter path from A location to B location, yeah, maybe travel times, maybe they use the travel times, maybe they use the travel cost. Yeah, then that depends on the problem itself. So when using a for loop to iterate through the metric, or by looking the linked list length, we are trying to see the degree of a particular. Yes, you can check the degree. I mean, because degree I have mentioned in the very second slide, which here is the number where is it in the very beginning, it's the number of edge. It's the number of edge. Then you can easily use then you can see, if you look at this, if you use the adjacency metric to check the degree, you always need to check the number of vertex. The number of iteration is the number of vertex. If you got 10,000 or 100,000 of vertex, then the number of iteration is 100,000. Then linked list is very simple. They just check the size of the linked list. If you store it earlier, if your data structure need to store the size of the linked list, you almost can instantly get the answer. If not, you also check just the number of degree. If the degree is 4, then you just need 4 iteration. You complete. So that is the degree. Then can a cyclic graph be said to have a Euclid circuit? Can I say yes? I think I can say yes. Let me confirm. Is a Euclid every edge, because Euler circuit is a circuit that use every edge of a graph exactly once. Every edge of a graph exactly one. That means it's a cycle, but it's a cycle graph to be said to have an Euclid. May not may not. If it's a cyclic graph, I can have a cyclic. I can have something like this, right? This is a cycle. Then this side is not, This is not, how to say, cyclic graph is to be have an Euclid circuit. The can I say yes or no? It's a different term. It's different term. Because if this is the things, are you saying, yeah, this is exactly because based on the definition of Euclid cycle, is a circuit that use every edge of a graph, every edge in the graph exactly once. Yeah, that is what the definition of Euclid circuit. Although it's beyond, I guess you learn in the discrete mathematics, but here we don't use it. Yeah, at this moment we don't cover this thing. But if you want to ask, yeah, I would say that is just talking about that every edge you use one, then that part is form a circuit, is form a Euclid circuit. And then whether inside got a cycle or not, maybe there's a cycle. Yeah, so it's the different issue, different things. Only use one. It's a different issue. Yeah. Any other question? If not, I will. Yeah, today can end earlier. Thanks. Wednesday I will talk about the maybe quick overview about the next lecture. Will be talk about this. I will talk about two. Basically, it's about the traversal of graph. Yeah, like I mentioned. Then in this module we only introduce two. Of course, there are a lot of way to travel. Just like travel in the tree, travel in the graph. There are a lot of way. We only introduce two. Don't assume there are only two. There are a lot of way to travel systematically. Yeah. So we only introduce the breadth first search and depth first search in the next lecture. Yeah. One is the level by level traversal. The other one is a greedy traversal. You are trying to travel as far as possible. Yeah, that is the depth first search. I will talk about it on Wednesday. Okay. That's all for today's lecture. Thank you for your attending. Goodbye.